So in this problem, we want to find the peak cooling power of a white roof of 100 meters square at early night time when the ambient air conditions are TA equals to 28 degrees and the relative humidity equals to 70%. Assume the emissivity of the roof material to be zero point 0.9 and the roof surface temperature to be, in the first case, A 50 degrees and in the second case, B 35 degrees. So, please, can any one of you share the link because someone is not able to answer? So, what should we do here? They gave us, for example, this is a typical problem that you can have in the exam. Even if sometimes I will give you empirical relations and you will use them directly in the problem. So just if you understand the concept, if I give you an empirical relation, you can directly apply. Okay? They gave you here that the heat transfer rate from the radiating surface to the sky is given by the following formula. So you have Q dot of radiation between the surface and the sky is equal to T surface minus T sky over the resistance between the surface and the sky. Already you are familiar with this type of formula. Okay, now the issue is that here we have a radiation combined with radiation effect that is not simple to calculate. Okay, so they gave you here how to calculate the resistance between surface and sky. Okay, and to calculate it, you need the H value, which is, if you want, it's like a coefficient lumping convective and radiation effect. Okay, and it's given by the following formula. So H between surface and sky is equal to epsilon surface times sigma times T surface plus 273.15 square plus T sky plus 273.15 square times T sky plus 273.15 plus T sky plus 273.15. So here they are giving you the formula of H. So this is empirical relation. You can directly apply. Okay. And all temperatures here are in degrees. So they should specify for you that all temperatures used are in degrees. Now to calculate T sky is given by epsilon sky times TA plus 273.15 to the power 4 and all the term to the power minus 4 minus 273.15. In addition to this, in order to compute epsilon of the sky is related to the dry bulb, the dew point temperature. Okay, we will explain now what is the dew point temperature, and you have an empirical relation at night time different than the empirical relation during the day. So this is a problem where you have all the given you need to have. You have all the empirical relations. All you have to do is to apply. Okay. Now let us see what is the dew point temperature. To understand this, we will go over the psychrometric chart and see by detail how to find different temperature in this chart. First, this is a very important chart, and you use it a lot in applications of radiation because you will see after that when we will study exchanger and desiccant wheels that this chart is of great help. Okay, so what is the idea about this chart? This chart represents the variation of the dry bulb temperature and the wet bulb temperature, in addition to the dew point temperature, with, if you want, these parameters will be function of each other. So for a certain point, you can have, if you determine, for example, two of the properties, you can find all of the other properties. Let us see how to deal with this chart. First, you have here, for this axis, your variable is called the humidity ratio. Okay, so here we have, what do we mean by the humidity ratio? Any idea? What is the humidity ratio?
Not the volume of water in the air or something like this.
Yeah, it is the mass of water vapor, okay, divided in the air over the mass of dry air. So humidity ratio, okay, represents the, because you know that air contains water in the vapor form, okay. So it's the mass of water vapor in kilogram over the mass of dry air in kilogram. Okay. Now, this is the first property in the psychrometric chart. Okay. The other properties, you have the dry bulb temperature, which is here along the x-axis if you want. Now, you have the wet bulb temperature given by the following curve. So this curve here, the values of temperature here correspond to the wet bulb temperature and also to the dew point temperature, and we will explain what is the difference between the two. Okay. So now, if you consider any point on this chart, okay, if you go directly downward, you get what is called the dry temperature. What do we mean by dry bulb temperature? It's the temperature that you are familiar with, that you measure with a manometer, with a device to measure temperature. So this is the temperature you are familiar with. Okay. Now, what do we mean? Please, can you mute your microphones, guys? Please, can you mute your microphone? Can you please mute your microphone? Okay. So here, whenever I have the dry bulb temperature, what is the meaning of the wet bulb temperature? Okay. The idea is that, you know, we said that air contains dry air. So when we have air, it's divided in a mass of air, it's divided into two parts. We have the water vapor and we have the dry air. Okay. So in air, we have a certain mass of water vapor and in general, you know that when if we have an additional amount of water vapor, this means that we are having more energy. In which form? More you have water vapor, you have energy in the air. In which form? You remember latent and sensible heat?
Yes.
Okay. So if you increase the content of water vapor inside air, this means that you are providing certain heat used in latent form, so it will be used to evaporate water. So the higher the water vapor content, the higher is the energy in air, because it will have energy in the form of latent heat. So higher this fraction, higher this fraction, higher the latent heat. Okay. Now, what is the idea of wet bulb temperature? If you have a certain air mixture, okay, and what you do is you increase, if you want, you increase the water vapor content, you increase the percentage of humidity here. So what will happen is that you will exchange between latent and sensible heat. Okay, so I will repeat. You have a certain amount of air, okay, that has energy in the form of sensible heat and latent heat. You can exchange from latent to sensible or from sensible to latent heat. So these two components of air, which are water vapor and dry air, can exchange heat between them. If dry air will lose sensible heat, it can transfer it to a form of latent heat by increasing the amount of water vapor inside air. Okay, so here look, if you follow this line like this, what is happening when you undergo this process? First, your dry bulb temperature is decreasing, as you can see. Okay, your dry bulb temperature is decreasing, so you are losing sensible heat. Okay, but on the other hand, you are gaining latent heat. Why? Because the amount of water vapor inside air is increasing. So the idea here is that you are transferring sensible heat in your mixture to latent heat. Okay, and this is what we call, if we reach the 100% relative humidity, this means that our air cannot sustain any more additional water vapor, and at this stage you will have condensation. Because look, when we will reach this stage, so I will clear everything so that it will be clearer. Okay, so if you move in this direction like this, what is happening? If you observe, first, your relative humidity is increasing, and when you reach this point, you are at the limit. You have 100% relative humidity. Where you can reach the 100%, if you follow this curve, okay, you have here 100%. This means that you reach the maximum capacity of your air in sustaining water vapor. It cannot sustain any additional amount of water vapor, and at this stage you will start to have the condensation. Okay, so we define wet bulb temperature if you want. It is defined as the dry bulb temperature when an air mixture will reach 100% relative humidity. Because as you can see, when you go from this point to this one, the dry bulb temperature will decrease because you are losing sensible heat. But this sensible heat is transferred to add the content of water vapor. Because look, if you want to see here, this is your initial, if you go to this axis, because this axis represents the mass of water vapor over the mass of air. As you can see, by going from point 1 to point 2, what is happening for the humidity ratio? The humidity ratio is increasing. So you are increasing the humidity ratio while you are decreasing the dry bulb temperature. So what is happening physically in this case? So when you go along the line of wet bulb temperatures, then you have transfer. So if you want, when I move, I will write it here. When I move along the wet bulb temperature line, okay, I am exchanging between sensible and latent heat. Okay, so if you want, I'm not losing any heat, but just I'm changing its form from sensible to latent, or from latent to sensible. Okay, so when you go in this direction of increased humidity ratio, so this is a line of wet bulb temperature. Okay, if you move in this direction, what is happening is that dry temperature is decreased. So as you can see here, when moving along this line, dry temperature is decreased while humidity ratio is increased. And of course, for the relative humidity, it's increasing, because these are the lines of relative humidity, these ones. So if you look at these curves, okay, this curve, so I will use this if it's clearer. This curve is for constant relative humidity. So as you can see, for example, here it's 60%. If I move along this curve, so I am moving along constant relative humidity. If I'm moving here, I am moving along a relative humidity of 40%. Now, if I move along this line corresponds to what? This line corresponds to constant humidity ratio. So in this case, the amount of water vapor is not changing if I move along this line. Okay? Now, if I move along this line, when moving along this line, what is the same as the dry bulb temperature, but if I go up, then I have increase of humidity ratio and increase of relative humidity. And if I go down, I have decreased the humidity ratio and decreased the humidity. Okay? Now, what is the dew point? If you look at this here, if you look at this line, when I go along a horizontal line, what is happening? My humidity ratio is not varying. So I am not gaining latent heat. No, latent heat is constant because the amount of vapor is the same. But when I go towards the left, I am losing energy or gaining energy? If I move like this, I am losing or gaining energy?
Losing.
Very
You
good.
are
I am losing energy. And I am losing energy in which form? In which form I am losing energy? Sensible
Thermal
or
and normal.
sensible. Very good. So when I move along the dew point line, okay, when I move along the dew point line, what is, I am losing or gaining energy. So my energy is not conserved like the wet bulb. When I move along the wet bulb line, I don't have loss of energy or gain. I just have exchange from one form to the other. This is what we call, you can say it's an adiabatic or isentropic process. And you will see after that an isentropic process is characterized by constant entropy. And we will introduce the entropy variable in the next chapter. Okay? So here, when I move along the dew point line, then I have constant latent heat. I have no change in latent heat, but only change in sensible heat. Okay, but only change in sensible heat.
الdew point line هو horizontal one.
Yes, dew point line هو horizontal. Okay.
كيف لقي هذا الdew point?
Sorry, I cannot hear.
How can you find the dew point?
How can the dew point? Okay. How to find the dew point? If they ask you for the dew point temperature, you go to the point. For example, in this problem, if you go back to the given, what are your given? Let us try to do for this problem. In this problem, they told us that the ambient air condition are TA equal 28 degrees and relative humidity equal to 70%. It's enough for you to know two properties of air to get any other properties. So if you know two of the properties, for example, here you know the temperature, and this is when they give the temperature and they don't specify, it's the dry bulb temperature. Okay, it's the dry bulb temperature. So 28 is the dry bulb temperature, and the relative humidity is 70%. Now you go to your chart, but you should pay attention for one thing here, that I don't know if you see it, but here you have a formula. So here, if you look here, this temperatures are in Fahrenheit. Okay, you should pay attention for this. All your temperatures are in Fahrenheit. So you need, because they gave you the temperature in degrees, the first step to do is to use this formula to find the corresponding value of temperature in Fahrenheit. So if you replace T degrees by 28, okay, you will get that the temperature in Fahrenheit is 82.4. So now, what are my conditions here? In this problem, the two properties I know are that T of A is density of air is equal to 28 degrees, which correspond to 82.4 Fahrenheit. So now, and the second property is that the relative humidity is 70%. So how to find the dew point temperature of air? What I should do is, first I should find the point of TA equal to 82.4 and the relative humidity equal to 70%. So I go to my chart. First, I take a line. This is the dry bulb temperature. This is 80. And as you can see, from 80 to 90, you have 5 divisions. So here you have 1, 2, 3, 4, 5. So each division is 2. So 82.4 is nearly here. Nearly here. Okay? Now, I will go upward with 82.4 until intersecting the 70% relative humidity. Okay? So how to find the 70% relative humidity? If you look here, this is the line of relative humidity. So this is 70. So this is the line of 70%. So your point of intersection between the two is here. This is the intersection point between the dry bulb of 82.4 and relative humidity of 70%. Once you determine the location of your point, okay, you can go up, okay, and you will here what you are interested in is the dew point. Okay, for the dew point, how you should move? You should move in the horizontal direction. If you want the wet bulb, you move like this, upward. Okay, but since you are interested in the dew point, you should move along the horizontal direction like this. Okay, and nearly this is your value. So this is 70, this is 72, so you are nearly in the middle. So you can say that your dew point temperature is equal to 71 Fahrenheit, and if you convert to degrees, it's nearly 22 degrees. Okay, so this is how we use the psychrometric chart to find the properties we need. Any question on the psychrometric chart? Okay.
No questions.
Okay, so now if I go back to my formulas, okay, what I should do, what I am interested in is I should find the radiation flux between the surface and the sky, okay, and I have everything given here. So T surface is given, T sky is given, sigma is the Boltzmann constant, I know it. Now I still need epsilon. Epsilon is given by the following empirical relation, okay? And you have two relations, one for night and one for the day, okay? And why we need to know this information? Because we should calculate the radiation during the day, the radiation during the night, and then we can find, if you want, per day, how much energy we are losing by radiation. Okay, so first, since we have two different formulas for epsilon between night and the day, and of course the temperature of the surface will vary and the condition of the sky will vary between day and night. If we go back to the question, okay, they asked for nighttime. So here they just asked for the cooling power at early nighttime. So we should use the formula for epsilon night. Okay. Then if you go to this slide, you will not use epsilon during the day. You will only use the following relation. Okay, because they ask only for the power of radiation during night. So you replace TDP by 22 degrees, okay, because here all temperatures are in degrees, okay, and you get epsilon. And now when you replace back epsilon, you can get H, and knowing H, you can find the resistance because you have the area, and replacing in this formula, you get the radiation heat transfer rate. Okay, So it's very simple. Once you find the dew point temperature, just replacement in the empirical relation. Now let us go to the calculation method. Okay, so as we said, the first step, from TA and relative humidity, we can get the dew point temperature. The dew point temperature is replaced in the empirical relation of epsilon sky. So TDP, replace it in epsilon sky, and we pay attention to replace it for epsilon sky during the night. Okay, and we get the temperature of the corresponding temperature of the sky. Okay, then replacing in our formulas, we can get the H coefficient, the resistance coefficients, and the radiation rate. Now pay attention. You find Q in watt, and since you want per unit area here, if you want your result per unit area, you divide by the total area of your surface, which is here 100 meters square. So in this way, you find the cooling power per unit area. This is your cooling power per unit area. Now, since they asked for two different temperatures, A, it's 50 degrees for the surface, and B is 35 degrees for the surface. And as expected, the radiation heat will be much higher when the surface temperature is higher. Okay? Because higher the temperature difference between surfaces, higher will be the radiation transfer. Okay? Any question for this?
Doctor, can you repeat why we use the dew point temperature?
Yes, because in this problem, okay, you have exchange by radiation, and as I told you in several problems that we have, we come up experimentally with empirical relations. So when I give you a problem, if I give you empirical relations, you should know how to work with. What they did here, they gave us condition of a surface and condition of ambient air. And we want to find what is the radiation heat exchange between the sky and the surface. Okay? And this is a complex phenomena. This is why from experimental work, we come up with empirical relations for the radiation exchange between a surface and the sky environment. Okay, so to find this exchange, they gave us empirical relations, function of the surface temperature, the sky temperature, okay, and if you want the ambient temperature, because you know that you have the ambient temperature is different from the sky temperature, because when they say sky, they mean very far from the surface. Okay, so here these are the empirical relations provided by the problem, so you don't have to know anything from before. In the problem, they give you this information. All you have to do is to try to apply the formulation here in your problem. As you can see here, inside the equation of H, which is the coefficient which will give you the resistance between surface and sky, you need to find the temperature of the sky to replace it here. Okay? And for the temperature of the sky, it is function of epsilon of the sky. So we should find epsilon of the sky in order to replace in this relation and find T sky. Then T sky is replaced here to find H. Okay? But from the empirical relation, epsilon sky is function of the dew point temperature. So in order to solve my problem, I should first find what is the dew point temperature of my ambient air condition. This is why I go to the psychrometric chart. Okay? Once I find dew point temperature, I can go back to my empirical relations. I begin by replacing here to find epsilon sky during night. Once I find epsilon sky during night, I replace into the formula of T sky here, I get T sky. Once I get T sky, I replace back here, I get H. And once I have H, I get the resistance. And once I have the resistance, I get the radiation flow rate. Okay?
Okay, thank you for circling back.
Any other question? Okay.
Why did we take it for the night again?
Why would you take it what?
During the night.
Because they asked in the question They asked estimate the peak cooling power of a white roof of 100 meters square at early night time. So it's during night time, okay? If they asked for daytime, we use the other relation, the second empirical relation. Okay? Let us see another problem, and the other problem also deal with this type of formulas. We want to compare the effectiveness of a white roof and an unpainted concrete roof by comparing the amount of radiative heat gain for one day. Okay? Here, in this problem, the analysis should be performed for a complete day. Because it's for a complete day, then we should do the calculation during the day and during the night to come up with the total radiative, if you want, exchange. And you will see if it will be positive or negative. So here we should consider day and night. Okay? Now, what are the given here? We have the average, first they gave us the total sunshine hours. Why they gave us the sunshine hours? For what purpose? For what purpose they gave us the sunshine hour? Who will tell me? So how would you know the number of hours of day and the number of hours of night? Yes, of course. But here, look, you have two, in your formulas, you have epsilon during day different than epsilon during night. So day and night, the difference between them are the presence of sun. So when you have sun, you consider that it's day. When you have no sun, it's night. So the total sunshine hours correspond to the total number of the day, 14. And therefore, in this case, the number of hours for night is 10 for a complete day. Okay? Now, they gave us the properties of the surface temperature at night and at day. Why we need them? Because here, as we said, we will calculate conditions during the day and during the night. So we have the surface temperature of the different, we have to compare here white and unpainted surfaces. Okay? This is why for both, they gave us the surface temperature during the day and during the night. Okay? Now, they gave us also the average ambient condition at night and the average ambient condition during the day. Because we will find, we will use the previous empirical relations. So we need to find the dew point. Okay? This is why they gave us the ambient condition during the day and during the night. In addition, we have that the average solar intensity during the day is 60 watt per meter square. Why did they give us the solar intensity? Who will tell me why they gave us the solar intensity? Look, when you want to compare the effectiveness of a surface, you should not only calculate what it is emitting, what it is radiating, but also you should consider what it is absorbing, because a surface will absorb heat and will radiate heat. Okay, so we want to see in total if the flux absorbed is equal, higher, so depending on the condition, to see if it will have an overall cooling effect or an overall heating effect. Okay, this is why we will calculate the total amount absorbed and the total amount radiated to know if it's an overall, it's cooling or heating. And if it's zero, we are in steady state condition. So it will not have any effect. No cooling, no heat. Okay? So, in addition to the solar intensity, they gave us the absorptivity and the emissivity of the surface. Okay? Now, let us try to do the analysis. What we should do first. For each surface, as we said, we have two phases, day and night. Okay? During the day, we have two processes going at the same time. During the day, we have what? We have the absorption. So we have the absorption of solar radiation, and at the same time we have what? You have the radiation. Okay? While during the night, do you have absorption of solar intensity?
No.
No, because you don't have sun. So during the night, you only have radiation. Okay? So if you want here, you have opposing effects. Absorption will lead to heating, while radiation will lead to cooling. Okay? So we will count absorption as a positive flux because it's entering the surface. Okay? And we will consider that radiation, we should add these two. These two, during the day and during the night, will lead to cooling effect. Okay, and they will be counted as negative because their effect is cooling. Okay, and they are considered as a negative because they are lost by the surface. So now, when we compute the absorption during the day, the radiation during the day, and the radiation during the night, we should add the three and we get the total value. If the total value is negative, this means that we have an overall cooling effect. If the total value is positive, this is not good because it will heat our space, especially in summer. And in summer, we desire to have cooling effect. Okay? And since it's a white roof, why we paint in white? In general, we paint in white, if you remember in the course material, one of the strategies to enhance radiation is to paint in white. So here we will compare the performance of a white roof and an unpainted roof, and we will see that the painting in white will enhance a lot the cooling effect. Okay? So let us start the calculation. First, as a first step, if we want to calculate the absorption flux, okay? How to calculate the absorption flux during the day? Let us take, for example, we will take as an example now the white surface, okay? But the formula will be the same for the unpainted surface. So for the white roof, if I consider Q absorbed, what is Q absorbed? How to calculate it? Yalla, who will tell me? What should I do?